So, hello everyone. I am Himanshu Mishra, and I am the PhD research scholar in the Department of Applied Mechanics, IIT Madras. So, last week we actually discussed question related to the heat exchangers. So, we covered the log mean temperature difference and the NTU problems in both parallel counter flow heat exchangers. So, this week we will start solving question related to the radiation heat transfer. So we will be solving some basic questions of radiative heat transfer such as irradiation, black body irradiation, and some spectral powers of the surface of the or the body. And we will also revise few questions from heat exchangers from the previous week, and we also look some couple of few questions from the evaporative heat transfer. So let's begin with the question number one. So this question in question number one, we have a small surface area A1 of 10 to the power minus 4 meters square, and it emits diffusively with a total hemispherical emissive power of given 5 10 to 10 to the power 4 watt per meter square. So we need to find the rate of emission intercepted by a small surface area and the irradiation on surface A2. So in this question, in the first part, we need to determine the rate of the emission, and we have given the surface area A2. So the radiation is emitted from A1 from at an angle theta 60 degree, theta 1 60 degree, and it is reaching A2, and we need to find the irradiation. So whatever the radiation will emit from the A1, it will incident on A2, so it will be a irradiation for A2 surface. That is the question part two of this problem. So in the part one, we are going to find the rate of the emission. So for the rate of the emission, we know that it can be given by so my radiation is going from 1 and incident on 2. So here omega is my solid angle. A1 is surface area, and we know that theta 1 is 60 degree, and I is my intensity. So I can find my intensity as the emissive power by pi. So we know this formula, and we know that the solid angle can be given as, sorry, it is 2. So I can put the expression of intensity and the solid angle in the equation, above equation. So here E1 is given as 5 multiply 10 to the power 4 watt per meter square. So I just need to put this value. And my theta 2 is given as 30 degree. So I just need to calculate the values here. This is my rate of heat transfer. So my rate of heat transfer is actually given by the equation number 1, which is a function of intensity, area A1, solid angle, and angle which the radiation is making when it come out from the surface. Now, since the solid angle is depends on the area A2 and the irradiation angle as well, so I can substitute these expression like expression for the solid angle and the intensity into the my heat equation, and then we just need to substitute the value. So this is my fundamental equation for the heat transfer due to the radiation, or if it is or if we have given the intensity, which is a direction dependent. And for the intensity, we know that it is given by the total emissive power divided by pi. So this expression is actually we get when we integrate the above heat equation, and it is direction and independent, and it is spectral in nature. That means it is not unique to one specific wavelength. So now for part B, we need to calculate the radiation on A2. So since it is a radiation which is coming from A1, it will incident to A2, and we know that irradiation is the total incident radiation which can received by any body. So irradiation of A2, that is whatever the radiation received by the body A2, we need to calculate that. So to calculate the radiation, so in our problem, the body 1 is actually emitting some radiation at theta 1, and whole of this radiation is actually reaching to the body 2 at an angle 30 degree, and this is my 60 degree. So we already found the heat transfer from this body through the radiation, and whatever the radiation is there, it will reach to body 2. So my irradiation is given by so we just need to calculate this, and this will be my radiation on body 2 from the surface 1. So this is a pretty simple, straightforward question where we need to use the first we need to find the heat transfer by radiation, which is a function of intensity and the solid angle, since there is a specific angle where the radiation is emitted. Now in the second part, whatever the radiation is emitted from the body 1, it will reach to some body which is body 2 at some specific angle, and that will be the irradiation. So let's move to the next question. So in this question, according to the directional distribution, the solar radiation incident on Earth's surface may be divided into two components. The direct component consists of a parallel rays incident at fixed zenith angle theta, and while the diffuse component consists of radiation that may be approximated as as being diffusively distributed with theta. So, okay, consider a clear sky condition for which the direct radiation is incident at theta 30 degree with a total flux of q direction is given as 1000 watt per meter square. Okay, and the total intensity of the diffusive radiation is 70 watt per meter square. What is the solar radiation at the surface? So in this question, so the body actually receiving heat by two sources. So let's say so the surface is actually representing receiving the energy, two kind of irradiation. So the first irradiation is coming at an angle theta degree, and the second by which this surface is receiving the radiation, it is diffusive in manner. That means it is not depend on the specific direction. It is actually coming from every side. So which makes roughly this hemispherical distribution of the radiation because it is a direction independent. So this is my irradiation, that's a G1, and this is my other irradiation, let's say G2. So my G1 is directional dependent, and G2 is diffusive. That means it doesn't depend on the direction, it is coming from every side, making roughly hemispherical surface around the surface, or body around the surface. So my total irradiation will be given as G1 plus G2. Now since I am receiving the G1 at an angle 30 degree, and it is given the amount of G1 which I am receiving is 1000 watt per meter square. You can write G1 as simply 1000 cos theta 30 degree cos 30, and G2 will simply be pi I2. So my intensity, diffusive intensity here is given as 70. So this is my diffusive intensity. So then my total irradiation, the total amount of energy radiation that I am receiving is given as So I just need to solve this, and I will get G equals 1086 watt per meter square. So this will be my total irradiation. So in this question, we are receiving the irradiation from different ways. The first, there are two ways in which we are getting the irradiation. First is directional dependent, which has some which is coming through one particular direction, making an angle theta, and other way is to directional independent way, where my radiation which I am receiving is diffusive in nature, and therefore the total amount of radiation which I am receiving is obviously the summation of all type of irradiation, and by taking the summation we will get the total irradiation. So it is also a pretty straightforward calculation. So let's move to the different question. So in this question, we have given the spectral distribution of radiation in the plot, and we need to define the total emissive power in the first part. The second part, we need to define the total intensity in the normal direction at an angle 30 degree. And in the third part, we need to determine the fraction of emissive power leaving the surface in the direction of pi by 4. So let's start with the first question. So we need to define the total emissive power, and in the plot we have given the emissive power at different wavelength actually, and we can see that at different ranges of the wavelength my emissive power is different. So to calculate the total emissive power, I need to calculate the summation of all the emissive power. So let's say this is my E1, and this is my E2, E3, E4, and so on. So the summation of all this emissive power over the ranges of wavelength will give the total emissive power here. So my E1 can be given as this will be my E1, and I am integrating the emissive power in wavelength from 0 to 5. So from 0 to 5, I am calculating my total emissive power. Emissive power. Similarly, for E2, my emissive power is this. So by taking the summation of all the emissive power, by taking the integration of each emissive power on a certain range of wavelength, we will get so I just need to put the value of emissive power of the specific region from the graph. So for E1, my E1 is 0, my E2 is 100, so my E2 is 100, and my E3 is 200, and my E4 is again 100, and my E5 is 0. My E1 is E2 is 100. My E3 is 200. My E4 is again 100. And my E5 is 0. So just taking the integration, it is a simple integration. So this will be 0, 0 plus on calculating this, we will get the total emissive power as 2000 watt per meter square. So the next question says that what is the total intensity of the radiation emitted in the normal direction at an angle of theta from the normal. So in the question it is written that it is a diffusive surface. That means the surface is actually emitting in all the direction. And in the question B, it is asked what is the radiation emitted at an angle theta direction. So here our surface is not actually emitting at a particular angle, let's say theta degree, which is given in the question. So since it is a diffusive surface, which is here mentioned in the question, surface is actually emitting the radiation in all the direction. So it doesn't matter if we need to calculate at 30 or 60 or even at 90. In all the direction, it is emitting the same radiation. So to calculate the intensity, which is directional independent here, we will be using simply this relation which we used in question number 1. So the total emissive power is 2000, and this will be my intensity here. So in case, let's say we don't have a diffusive surface, let's say the surface is actually emitting the radiation at an angle 30 degree, which is given in the part B of the question, and surface is not a diffusive nature, which unlike mentioned in the question. In that case, we can use this relation to find the intensity. So this is for when the radiation is directional dependent. Radiation which is emitting from the surface is directional dependent. But since the surface is diffusive, which is mentioned in the question, it doesn't matter from what direction we are considering. It is always, so intensity will always the same in all the direction. So therefore we can use just a simple relation here for the diffusive nature. So this relation is actually come from this relation itself. When we integrate this relation in theta, so we are making the expression directionally dependent. So if you integrate this expression from 0 to some theta, you will get dq, which is diffusive in nature. And you integrate again this expression and lambda. So if you I'm integrating in theta and in lambda. So this expression, the heat transfer equation, is become diffusive as well as spectral. That means it will emit all the radiation. We have actually considered the all component of all wavelength of the radiation, and it is also directional independent. It is a diffusive. So by solving this, we will get this relation, which is a relation of intensity or the emissive power, which is a diffusive in nature. And if it is a directional dependent, then we can use this relation to find the heat transfer. So let's move to the different question. So in this question, we need to identify the correct statement. So we have given the four options, and we have given the chart which actually tells the heat transfer in boiling, which is varying with the temperature difference. So my temperature difference is given as the temperature of the surface and the saturation temperature, and in the y-axis it is heat flux is giving, which is varying with the temperature difference. So in this figure, the first A region says that A option says that region CD falls in the transition boiling region. So this region is actually the transition boiling region, which is true. This is my nucleate boiling region, and once we cross the sea, we got transferred to the point E, and by doing a careful experiment, sometimes we also goes through the transition boiling region and then towards E. So this is my region where the breakdown of my system happens due to the excessive temperature. So yeah, my option A is correct because this is my transition boiling region. The option B says that the stirring and agitation caused by entrainment of the liquid to the heat surface is primarily responsible for the increased heat transfer coefficient and heat flux in the region of nucleate boiling. So this region is my nucleate boiling region. So as the heat flux is increasing with the temperature, my heat transfer coefficient will also increase, and this is because as we keep heating the liquid, so this is my liquid in beaker, my bubble, it generates some bubbles, and these bubbles actually move to the upper surface, and it will cause the stirring, agitation, and some chaotic behavior inside the fluid. And since due to motion of this large number of bubbles, it will increase the heat transfer coefficient, and it will increase the heat transfer rate till here, till somewhere here, and after that the heat transfer coefficient will start decreases. So yeah, from point A to point, let's say A star, my heat transfer coefficient will increase due to the stirring effect of the bubbles that produce in the nucleate boiling region. So my option B is also correct. So option C says the nucleate boiling is the most desirable region in the practice because high heat transfer rates can be achieved in this region. So since my heat transfer coefficient increase in the nucleate boiling region, of course my heat transfer will also increase due to that, and therefore this nucleate boiling is the most desirable region, of course, because of the high heat transfer rate. So in this region, we usually avoid this region because there the breakdown of my system usually happen due to the high temperatures. In that case, my platinum wire or whatever system I'm using to produce heat, it will break down due to the high temperature because it will reach its melting temperature. And also the transition region is very difficult to attain in the experiment. So when the first experiment is carried out, researchers actually identify the nucleate boiling region and the region D to DE, and they did not actually find the transition boiling. So for this we need very sophisticated experiment, and also the heat flux is decreasing here in the transition boiling. So here actually the some line of vapor actually created at the surface, which actually decrease the heat transfer coefficient, and therefore my heat transfer rate will also decrease. So Basically, these two regions are unavoidable and does not desire, because here my heat transfer rate or my heat transfer coefficient decreases because of the formation of the bubble or the air layer at the surface. And at DE, here at DE, the system breakdowns usually happen due to very high temperature. So nuclear boiling is only the region where my heat transfer rate or the heat transfer coefficient increases, and it is therefore the most desirable region. So again, my option C is also correct. So the correct option is D, which indicates that all my options are correct. So let's move to the different question. So in this question, we have given the dark surface of ceramic stove top may be approximated as a black body. The burners which are integral with the stove top burners, are heated from below by electric resistance heater. So consider a burner of diameter D 200 mm operating at a uniform surface temperature of 250 degrees Celsius and the ambient temperature of 20 degrees Celsius. Without a powder pan on the burner, what are the rates of heat loss by radiation and convection of the burner? If the efficiency is associated with 90 energy, 90%, what is the electric power requirement? At what wavelength the spectral emission is a maximum? So here we need to calculate the rate of heat loss as well as the power, and we have given a burner, and the mode of heat transfer to the burner is convection as well as the radiation heat transfer. So whatever will be the total rate of heat loss, it will be due to my radiation heat transfer as well as my convection heat transfer. So my radiative heat transfer is actually given by the Stephen Boltzmann law, and it is also given that I can assume my burner as a black body, so I don't need to take care of emissivity and all. So my heat transfer due to radiation is given by so here my emissivity is 1 since it is a black body radiation. Sigma is my Stephen Boltzmann constant. And just we need to substitute the values. And we need to write the temperature, which is 250 degrees Celsius. We will convert into the Kelvin. So on solving this equation, we will get the heat loss due to radiation as 133 watt. Now I need to find the heat loss due to convection also. So we know that the heat loss due to convection is given by the Newton's law of cooling. So we have solved plenty of problems the last week related to this. So to get the heat loss due to the convection, we need to find the heat transfer coefficient. So we have given the temperature, surface temperature and the ambient temperature. We have given the area, but we need to find this heat transfer coefficient. And to find this, I am using the Nusselt number correlation for that. So since it is not given in the question that there is a motion of air because of a pump or some by external means, I will be assuming this heat transfer due to the natural convection. So for the natural convection, my Nusselt number will be given as this is my Rayleigh number. And my Rayleigh number is I can find my length as the ratio of the surface area and the parameter. So we have actually solved such question in the last few weeks where we actually need to calculate the thermal expansion coefficient and then Grashof number or the Rayleigh number. And from the Grashof and Rayleigh number, we can calculate the Nusselt number, which is given by some correlation depending upon the nature of flow. And from the Nusselt number, we know that we can easily found the heat transfer coefficient. So my Rayleigh number is given as this is my beta. So beta can be found out inverse of temperature and inverse of the mean temperature. And my mean temperature is given as surface temperature and ambient temperature. Just remember that these temperatures should be in Kelvin. So my mean temperature should be in Kelvin and my beta is just a reciprocal of the mean temperature. So this is my length, which we can obtain from the ratio of the surface area to the perimeter. So my Rayleigh number would be 6.35 10 to the power 5. Now I can find my Nusselt number or that my heat transfer coefficient is so I can write my Nusselt number as HK by L. So I'm directly writing the expression for the heat transfer coefficient here. I just substitute the value of the required parameters. I will get my heat transfer coefficient will be on calculating about 10.5 watt per meter square Kelvin. So now we got the heat transfer coefficient. I can just use the Newton's law of heat transfer to find the heat transfer due to convection. So my heat transfer due to convection is 75.7 watt. So the total heat loss from the system will be heat loss due to radiation plus heat loss due to convection so it will be given as this will be 208.7 will be my total heat loss due to the convection as well as the radiation. Now to find the power requirement, we have given the efficiency which is 90%. So the power will be 232 watt. So in the third part of the question, we have asked that at what wavelength my spectral emission is a maximum. So for this, we will be using the Vane's law. Which is so the temperature we have given is 250 degree. So I will be converting into Kelvin, and this will be my maximum wavelength that the system could emit. So my system is given at the surface temperature of 250 degrees Celsius, and we know that if the surface has the temperature above the 0 Kelvin, it will always emit some kind of a radiation, and we have asked the maximum radiation. So it will be given by the Vane's law, which is actually is this. So this is my maximum wavelength which surface of a temperature T can emit. So a surface with a temperature of 250 degrees Celsius can emit a wavelength of 5.54 micrometer. So this is the required maximum wavelength that our system could emit because of the temperature, the given temperature 250 degrees Celsius. So in this question, we have given a burner, and the surface and ambient temperature was given, diameter is given, and we need to calculate the total heat loss that is occurring in our system. So in this system, there will be the heat loss due to the convection as well as the radiation which is mentioned. That means there is a flow of air across the burner, which actually taking the heat away from the burner through convection process. And since the burner is at temperature 250 degrees Celsius, it will have at higher temperature we have to consider the fact of radiation heat transfer also. So there will be the heat loss due to the two components, due to the two modes, radiation heat transfer as well as the convection heat transfer. So we calculate the radiation heat transfer, which is a straightforward calculation, especially for the black body, by using the Stephen Boltzmann law in the equation 1. To calculate the convective heat transfer, we actually need this heat transfer coefficient. And to calculate the heat transfer coefficient, we need to identify whether the flow is forced, whether the heat transfer is forced, convection, or the free convection. Once you identify any of this, then you need to identify for the force case that whether it is in laminar or turbulent case. So according to this nature of the flow, you will be using the Nusselt number correlation. So the Nusselt number correlation is actually differ for all case, like for the laminar case, for the turbulent case, as well as for the free case. So depending on the nature of the problem you identified here, you will be using the Nusselt number correlation to find the Nusselt number and then the heat transfer coefficient. Once you get the heat transfer coefficient, you can use this expression to find the convection heat rate. So the total heat rate then would be defined as the heat rate due to the radiation as well as the heat loss due to the radiation as well as the heat loss due to the convection. So this will be my total heat loss. The second part of the question, we have asked to determine the maximum wavelength that system can emit. So according to the Vane's law, it is actually depends upon the temperature only. So our surface temperature is given as 250 degrees Celsius. That means the maximum wavelength that it could emit can be easily obtained by the Wein's law here. And we found it is 5.54 micrometer. So moving to the next question. The directional total emissivity for non-metallic materials approximated as epsilon n cos theta, where epsilon n is a normal emissivity, and show that the total hemispherical emissivity for such material is 2/3 of the normal emissivity. So we have given the emissivity here, directional emissivity epsilon theta, and we need to calculate the total hemispherical emissivity and show that this hemispherical emissivity is 2/3 of the epsilon n. So our total emissivity can be given as this is my directional emissivity theta, and this is my normal component of emissivity. And my total emissivity is given as here. So this is my solid angle actually. So my directional emissivity is actually E theta. So in the earlier question I have said that my power is actually proportional to some intensity cos theta sin theta. So this is actually the directional dependent heat transfer, and if you want the diffusive heat transfer, which is directly directional independent, then you need to integrate it with theta to 0 in d theta. So now this, after integration, you will get let's say heat transfer rate which is diffusive in nature. So this is exactly the same thing we are doing. So E theta is our directional dependent emissivity, and we need to find the total diffusive emissivity here, which is given by the same expression. We need to actually integrate this expression from pi/2 to 0 to get the diffusive emissivity. So I can just put the value of epsilon theta as this is my epsilon theta, which is given in question. So I just need to integrate this. So after putting the value here, so I will get my total emissivity as 2/3 of the normal emissivity. So this is what we need to show actually here. Show that the total hemispherical emissivity is 2/3 of the normal emissivity. So we have given the directional emissivity and we integrated from theta to 0 to find the total hemispherical emissivity, which is directional independent, and we found that after integration that my total diffusive emissivity is 2/3 of the normal emissivity. It's a straightforward again. So let's move to the different question. So in this question, a condenser of large steam power plant is a heat exchanger in which steam is condensed to liquid water. Assume the condenser to be a shell and tube heat exchanger and having the 30,000 tubes and the diameter is 25 mm and steam condenses their outer surface with convection coefficient of 11,000 and the heat transfer rate is given. So the heat transfer is actually due to the cooling water. And the mass flow rate of the cooling water is 10 to 10 to the power 4 kg per second. And flow rate per tube is 1 kg per second. The water enters at 20 degrees Celsius while the steam condenses at 50 degrees Celsius. What is the temperature of the cooling water emerging from the condenser? And what is the recoil length L? So this is the problem of the heat exchanger with evaporation. So we have solved the plenty of heat exchanger problem in which we actually found out the geometry of the heat exchanger by using both NTU and the log mean temperature difference. So in the first part of this question, we need to find the temperature of the cooling water or the cooling fluid which is coming out of the heat exchanger. So for this, we will be using the heat transfer relation. So we have given the heat transfer, we have given the mass flow rate. So my heat transfer is given as 2 10 to the power 10 to the power 9 and my mass flow rate is given as 3 10 to the power 4. And I need to find the outlet temperature of this fluid. So we just put the values. And we found the outlet temperature as 36 degrees Celsius. Now in second part of the question, we need to calculate the length of the heat exchanger. So we actually earlier in the previous weeks we actually calculate the length of the heat exchanger by both log mean temperature difference as well as by using the NTU method. So we know how to calculate the length. So in this problem, I will be calculating length by the NTU method. So by NTU method, we calculate the length by using this relation. So basically, we are looking for area. We have given the U, which is overall heat transfer coefficient, and we have given the C min. But we need to find first NTU to use this relation. So first we need to find the NTU and from this we will finding the area and we can get length from the area. So this is a regular way which we actually used in the last week also. So to find the NTU, we need effectiveness, which again is not given in the question. And to find the effectiveness, we know that effectiveness is the ratio of the actual heat transfer as well as the maximum heat transfer. So we know the actual heat transfer actually. We know the actual heat transfer, which is 2 10 to the power 9, and we can calculate the maximum heat transfer. So basically here I'm going backwards. So the usual route that we follow last week is first to write this equation NTU equals UA by C mean. We need to calculate the area or the length, let's say. So that we first need to find the NTU, and for NTU we need effectiveness, and for effectiveness we need the maximum heat rate. So basically we are going in the reverse direction. And we can still follow reverse. For the maximum heat rate, we require the inlet temperature of hot fluid as well as the inlet temperature of cold fluid. So we have given the heat transfer coefficient of the outer surface. That means we need to calculate this overall heat transfer rate also. So let me summarize this. We need to find length. This will get from the area expression. And the area expression will be getting from the NTU method. For the NTU is unknown, and the overall heat transfer coefficient is unknown. Now this we can easily find if we have given the internal heat transfer coefficient as well as the outer heat transfer coefficient. So this we have given, this we have not given. So to find the internal heat transfer, we will be using the Nusselt number correlation. Once we get the internal heat transfer by using the Nusselt number correlation, we can find the overall heat transfer. Now to find the NTU here, we need effectiveness, and for effectiveness we need maximum heat transfer as well as the actual heat transfer. So we have given the actual heat transfer. We need to find the maximum heat transfer, and the maximum heat transfer we can easily find if we are given the inlet temperature of hot and cold fluid. So we can find this, we can find the maximum heat transfer from this, and then we can find the effectiveness, and from the effectiveness by using the graphical method or the correlation we can find the NTU. And I already discuss how to find the overall heat transfer. So let's went one by one. So let's first find the overall heat transfer U. So we know that the overall heat transfer is given by summation of the inverse summation of the inverse of summation of the internal and outer heat transfer coefficient. We have given the outer heat transfer coefficient, but we don't have the internal heat transfer coefficient. So this internal heat transfer coefficient actually will be given by the Nusselt number correlation. And to apply the Nusselt number correlation, we need to identify the nature of the flow, whether the flow is in laminar or in turbulent region. For this, we need to calculate the Reynolds number. So since we are given the flow rates, I will write the Reynolds number in terms of flow rate. This is my Reynolds number, and on calculating, my Reynolds number is 59,561, which is obviously more than the critical Reynolds number. So for Q, my critical Reynolds number is around 2400. So that means my flow is turbulent in nature. So I need turbulent Nusselt number correlation to find the internal heat coefficient, heat transfer coefficient. So my turbulent Nusselt number correlation we know is so we actually solved plenty of such problems in past weeks when we were discussing about the question related to force and force heat convection. So we just need to put the values. My Reynolds number is, we already found this. And Prandtl number can be given from the properties. So my Nusselt number is 308. And I can get my internal heat transfer by simple relation of the Nusselt number. So my internal heat transfer coefficient is 7543 watt per meters per Kelvin. So my overall heat transfer coefficient is 1 by 7543 plus 1 by 11,000. This is my outer heat transfer coefficient. So my overall heat transfer coefficient will be 4474. This is my overall heat transfer coefficient. Now I can use my NTU relation, but first we need to find the NTU itself. So to find the NTU, we need effect. We can get from effectiveness correlation or the plot versus effectiveness and NTU that we have discussed how to use this plot. So this is the first way. The second way is to use a correlation of effectiveness and NTU. It actually depends on the nature of the heat exchanger we have given. So for the parallel flow heat exchanger, we can just directly use the correlation, even for counter heat exchanger also. But for the cross flow heat exchanger, we may need to use the graph of effectiveness versus NTU, which is we have already discussed. So we need the effectiveness, which is given by the ratio of actual heat transfer and the maximum heat transfer. So we already given the actual heat transfer, and the maximum heat transfer is given as my minimum heat capacity is, which is 1.25 10 to the power 8 watt per Kelvin. So this is my minimum heat capacity. So my maximum heat transfer is, I'm using this relation. So this is my maximum heat transfer. So effectiveness can be given as, my actual heat transfer is given as 10 to the power 9 watt. So 0.532 is my effectiveness, And for the cross flow heat exchanger, we will be using graph. And from the graph, we can directly get the NTU as 0.759. To know how to use the graph, you can see the last video where I identify the value of NTU from the effectiveness versus NTU plot for the cross flow heat exchanger. And I also actually describe where to use a correlation and where not to use a correlation. So once we got the NTU, and we also actually found the overall heat transfer coefficient, we can easily find the geometry of the heat exchanger. I mean, size of the geometry of the heat exchanger. So my area is, and we need to identify length. So my length will be given as 2 pi d multiplied by n. So here I am multiplied by n because in the question we have given there are 30,000 tubes. So this will be, so I am multiplying by 30,000 tubes. So this NTU relation for each tube, and by multiplying with the total number of tubes, we can determine the total length of the heat exchanger. So we just need to put the values. So my Nusselt number, this is my heat capacity rate. This is my overall heat transfer coefficient. This is my total number. So just by calculating or solving this, my length would be 4.51 meter. So this is actually an involved question. We need to find so many things in this question. So I will revise here. So in this question, we need to find the length of the heat exchanger, and we use the NTU method to find the length. So to find the length using NTU method, we actually use this relation. But the overall heat transfer coefficient is unknown. The NTU is also unknown. So first we found the overall heat transfer coefficient, which is a function of my internal heat transfer coefficient as well as my outer heat transfer coefficient. Now we are given the outer heat transfer coefficient, but not the internal heat transfer coefficient. So we use the Nusselt number correlation to find this. And the Nusselt number correlation is actually depends on the nature of the flow, whether the flow is in laminar or turbulent state. So by using the Nusselt number correlation, we found the internal heat transfer coefficient rate and then the overall heat transfer coefficient rate. For NTU, we found the effectiveness, which is a function of the actual heat transfer as well as the maximum heat transfer. So first we found the maximum heat transfer, and then we found the effectiveness. Effectiveness can be found from the correlation, effectiveness and Nusselt number correlation, or from the graph. So since we have given the cross flow heat exchanger, for the cross flow, it is suitable to use the graph. We can use correlation in case of the parallel or the counter type heat exchanger. So once we get the effectiveness, we got the NTU as well, and we just use the simple NTU relation to find the geometry. So this is it for today. So for today, we actually discussed some basic question of the radiation heat transfer. We actually look one problem related to the evaporation, and we also recollect the problem of the heat exchanger, where we actually found the geometry of the heat exchanger by NTU method. And in one of the questions, we actually found the total heat loss due to the convection as well as the radiation heat transfer. So next week, we will solve some more problems related to the radiation heat transfer. So yeah, that's it for today. Thank you. You can watch this video to revise or to see my lecture, and I will also upload this slide. You can check the slides to the link which is given to you. Thank you.